On March 4, 2018, Stephen Hawking approved the final corrections to a 14-page paper. He did this the way he had done everything for the last several years of his life, by twitching a single muscle in his cheek. An infrared sensor mounted on his glasses detected the movement, which selected a character on a screen, which eventually, after many minutes, formed a word. It took him several minutes to produce a single word. By this point, the paper was called A Smooth Exit from Eternal Inflation. It was co-authored with Thomas Hertog, a Belgian physicist who had been working with Hawking for 20 years. Hertog was the corresponding author. He would be the one to shepherd it through peer review. Hawking would not live to see it published. 10 days after approving those corrections, on March 14th, he died in his home in Cambridge. He was 76 years old. The paper was published 6 weeks later in the Journal of High Energy Physics. 14 pages. Open access. Anyone on Earth could read it. It received a brief flurry of media attention, mostly because the most famous scientist in the world had just died, and journalists needed something to write about. The Sunday Times called it potentially his most important scientific legacy. The Telegraph suggested it might have earned him the Nobel Prize that had always eluded him. A few outlets claimed it would prove the multiverse or detect other universes. Within a week, other physicists began pushing back. Frank Wilczek, a Nobel laureate at MIT, called it heavy on speculative assumptions with no concrete predictions. Neil Turok, who had once collaborated with Hawking, said he was puzzled as to why Hawking found the picture interesting. Katie Mack, a cosmologist at North Carolina State, pointed out that the paper was not giving any new kind of observable signature different from other models. And then the world moved on. The paper settled into the quiet archive of theoretical physics, cited occasionally, discussed rarely, its implications never seriously reckoned with by the broader public. You have almost certainly never heard anyone talk about what it actually says. That should bother you, because what it says is not a minor technical correction to an obscure corner of cosmology. What it says, when you follow the logic all the way down, is that the laws of physics are not real in the way you think they are. They are not eternal. They are not written into the fabric of the universe. They did not exist before the Big Bang, and they are not guaranteed to exist tomorrow in their current form. They are patterns, emergent, evolving, contingent patterns that arose with the universe and could, in principle, change. Stephen Hawking spent the last 20 years of his life building toward that conclusion. He published it. He died. And the physics community, the people who should have been grappling with this, responded with the intellectual equivalent of a polite shrug and a change of subject. This is the story of what Hawking actually found, why it matters more than almost anything else in modern physics, and why the people who understand it best are the ones least willing to talk about it. But to understand what drove Hawking to this point, you need to know something that almost nobody outside theoretical physics is aware of. Stephen Hawking repudiated his own most famous work, not in some private moment of doubt, not in some offhand comment at a dinner party. He summoned a colleague to his office, looked him in the eye, and declared that his masterwork, the book that had sold over 25 million copies, the book that had made him the most recognized scientist on the planet, was fundamentally wrong. That happened in 2002. The colleague was Thomas Hertog, a young Belgian physicist who had just finished his PhD under Hawking's supervision at Cambridge. Hertog describes the moment vividly. Hawking's eyes, he says, were radiant with excitement, and the words that came through that synthesized voice, the voice the whole world recognized, were devastating. I have changed my mind. My book, A Brief History of Time, is written from the wrong perspective. Think about that for a moment. A Brief History of Time was not just a bestseller. It was a cultural phenomenon. It sat on coffee tables and nightstands in millions of homes across the world. It shaped how an entire generation understood cosmology. Its final line, the one everybody remembers, promised that discovering a complete theory of physics would be the ultimate triumph of human reason. For then we would know the mind of God. And Hawking, the man who wrote that line, was now saying the entire framework was wrong. Not the details, the perspective, the foundational assumption that there existed a God's eye view of the universe, a set of eternal laws written into reality from the outside, waiting to be discovered by sufficiently clever primates. That assumption, Hawking was saying, was the mistake. And what he arrived at instead, over the next 16 years, was not a better version of the same idea. It was something closer to the end of the idea itself, the end of eternal law, the end of the search for the mind of God. Not because the search failed, but because there was never a mind to find. That is what the 14-page paper was about. And that is why nobody wanted to deal with it. But the paper did not emerge from nowhere. Hawking did not wake up one morning and decide the laws of physics were emergent. He arrived at that conclusion because he was trying to solve a crisis that had been growing inside theoretical physics for decades, a crisis that by the early 2000s had become so severe that some of the smartest people in the field were privately wondering whether their discipline had hit a wall, whether physics, as a project capable of producing testable predictions about the universe, was effectively over. And the strangest part of this crisis is that it was created by one of the most celebrated achievements in the history of cosmology. The very theory that was supposed to explain everything had accidentally proved that nothing could ever be explained again. That theory was eternal inflation. And to understand why it broke physics, you need to understand what inflation was supposed to fix. In 1980, a young particle physicist at MIT named Alan Guth was working on a problem that had been nagging cosmologists for years. The universe, as observed, had several properties that the standard Big Bang model could not explain. The cosmic microwave background radiation, the afterglow of the Big Bang, was astonishingly uniform. No matter which direction you pointed a detector, the temperature was the same to within 1 part in 100,000. That should not be possible. Regions on opposite sides of the observable universe are separated by 93 billion light-years. In the standard Big Bang timeline, light had not had enough time to travel between these regions since the beginning of the universe. They had never been in causal contact. They had no way to exchange energy, no mechanism to equilibrate their temperatures, and yet they were at exactly the same temperature. That was the horizon problem. There was also the flatness problem. The geometry of the universe appeared to be flat, or very close to flat, which required an extraordinary degree of fine-tuning in the initial conditions. Even a tiny deviation from perfect flatness in the first fraction of a second would have been amplified by the expansion of the universe into either a violently curved, rapidly collapsing space, or an empty, featureless void. The fact that the universe was still approximately flat after nearly 14 billion years meant that the initial density had to be tuned to an accuracy of roughly 1 part in 10 to the 62nd power. That is not a number that arises naturally. That is a number that demands an explanation. Guth's solution was elegant. He proposed that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. In approximately 10 to the negative 36th of a second, the universe doubled in size at least 60 times, growing from something smaller than a proton to something larger than the observable universe. This inflationary period solved the horizon problem because regions that appear disconnected today were actually in causal contact before inflation stretched them apart. It solved the flatness problem because inflation drove the geometry toward flatness, the way inflating a balloon smooths out its wrinkles. And it solved the monopole problem, which had to do with hypothetical magnetic monopoles that should have been produced in enormous quantities in the early universe, but have never been observed. Inflation diluted them to undetectable levels. It was a beautiful theory. It made specific testable predictions about the cosmic microwave background that were later confirmed with remarkable precision by the COBE, WMAP, and Planck satellites. Guth was celebrated. Inflation became the standard model of early universe cosmology. It appeared in every textbook. It was, by any reasonable standard, one of the great triumphs of 20th century physics. And then someone noticed that it could not stop. In 1986, the Soviet-born physicist Andrei Linde, who had independently developed his own version of inflation, called chaotic inflation, demonstrated something troubling. The quantum fluctuations that drive inflation are random. In most regions of space, inflation eventually ends, and a pocket universe like ours forms. But in some regions, the fluctuations are large enough to keep inflation going, and because the inflating regions expand exponentially while the non-inflating regions do not, the volume of inflating space always grows faster than the volume of space that has stopped inflating. The result is that inflation, once it starts, never stops. Globally, the universe keeps inflating forever. The American physicist Alexander Vilenkin had arrived at similar conclusions as early as 1983. This was not a bug in the theory. It was a feature. Almost all models of inflation lead to eternal inflation. It is not something you have to add or assume. It falls out of the mathematics naturally. As Guth himself would later put it, anything that can happen will happen an infinite number of times. And that is where the crisis began. Because if inflation is eternal, it does not produce one universe. It produces infinitely many. Each pocket universe that forms when inflation locally ends can have different physical constants, different particle masses, different fundamental forces. The speed of light might be different. The strength of gravity might be different. The number of spatial dimensions might be different. When you combine eternal inflation with the string theory landscape, which catalogues roughly 10 to the 500th possible configurations of the fundamental laws, you get an infinite fractal-like structure of pocket universes, each one governed by its own version of physics, an infinite multiverse. This might sound like an exciting expansion of our understanding. It was the opposite. It was the death of prediction. Because if infinitely many universes exist with infinitely many different physical laws, then any observation is consistent with the theory. You cannot calculate the probability of our particular universe, because doing so requires comparing infinite sets And there is no unique way to do that. This is called the measure problem. And after decades of effort by the best mathematical physicists in the world, it remains unsolved. The anthropic principle was offered as a way to salvage the situation. We observe the physical constants we observe. The argument goes, because only those constants permit observers like us to exist. Steven Weinberg used this reasoning in 1987 to make a rough prediction of the cosmological constant, which was later confirmed, and this was taken by many as a vindication of anthropic reasoning. But Hawking saw what the anthropic principle actually was. It was not a solution. It was a surrender. If your theory predicts everything, it predicts nothing. If any outcome is consistent with the theory, then no observation can ever falsify it. And a theory that cannot be falsified is not science. It is philosophy dressed up in equations. Hawking said it directly. If the scale of different universes in the multiverse is large or infinite, the theory cannot be tested. Avi Loeb, the Harvard astrophysicist, echoed the same concern. The virtue of traditional physics, Loeb said, is that its theories could be falsified by experiments. Science is a learning experience. If we give up on the possibility of falsifying our ideas, then we will not learn anything from experiments. This is the crisis that was already well advanced by 2002, the year Hawking told Hertog that a brief history of time was wrong. The most celebrated achievement of late 20th century cosmology, inflation, had accidentally produced a framework in which science could no longer function. The theory explained everything, which meant it explained nothing. And the physics community's response to this was not alarm. It was not a crisis summit. It was a slow, quiet accommodation. Many physicists simply accepted the multiverse and the anthropic principle as the best available framework and moved on. Others focused on subfields where testable predictions were still possible. A few, like Hawking, refused to accept it. And the reason Hawking refused was not just intellectual, it was personal. The multiverse crisis had not been caused by some external force. It had been caused, in part, by his own work. The no-boundary proposal, the idea he had published with James Hartle in 1983, was one of the mathematical engines that powered the infinite multiverse. When you combined the Hartle-Hawking wave function with eternal inflation, you got exactly the fractal infinity that rendered physics unfalsifiable. Hawking's own most celebrated contribution to cosmology was part of the machine that was killing cosmology. And he knew it. The no-boundary proposal itself is worth understanding, not as background context, but as the loaded gun that Hawking spent the rest of his career trying to disarm. In 1981, at a conference hosted by the Pontifical Academy of Sciences at the Vatican, Hawking stood before an audience that included Pope John Paul II and made a declaration that remains one of the most audacious statements in the history of physics. There ought to be something very special about the boundary conditions of the universe, he said. And what can be more special than the condition that there is no boundary? The full mathematical treatment came 2 years later, published in December 1983, in Physical Review D, Volume 28, under the title Wave Function of the Universe. Hawking's co-author was James Hartle, an American physicist at UC Santa Barbara who had earned his PhD under Murray Gell-Mann at Caltech. Colleagues called Hartle a man with no boundaries, which was both a joke about his research and an accurate description of his intellectual range. He would go on to win the Einstein Prize from the American Physical Society in 2009. What they proposed was breathtaking in its ambition. They wrote down a formula for the wave function of the entire universe. Not a single particle, not a single field, the entire cosmos, all at once. The formula used Richard Feynman's path integral approach, which means it summed over every possible history the universe could take, every possible geometry, every possible configuration, all of them contributing to a single quantum mechanical amplitude. The trick that made this possible was a mathematical technique called the Wick rotation, which replaces the time coordinate with imaginary time. When you do this, the geometry of space-time transforms from Lorentzian, the normal kind with a distinction between space and time, to Euclidean, a kind where time and space are interchangeable. In Euclidean space-time, you can have geometries that are smooth and closed, like the surface of a sphere. There are no edges, no singularities, no boundaries. The universe in this picture is shaped like a shuttlecock, a badminton birdie. It has zero diameter at the bottom and gradually widens as you move upward. The bottom is not a boundary. It is a smooth cap, like the south pole of the Earth. Time does not begin at some sharp edge. It smoothly caps off. It emerges from nothing, or rather from a geometry where the distinction between something and nothing does not apply. Hawking's famous analogy for this was simple and devastating. Asking what came before the Big Bang, he said, is meaningless. It would be like asking what lies south of the South Pole. There is no south of the South Pole. The question has no answer, because the question does not refer to anything real. Similarly, if time is a smooth, bounded surface, there is no before the beginning. The beginning is not an event in time. It is the point where time ceases to be a meaningful concept. This was the framework that A Brief History of Time popularized for millions of readers. And it was beautiful. But it had a fatal flaw that only became visible when you ran the equations in the regime of eternal inflation. When you summed over all possible histories in the no-boundary framework, you did not get one universe. You got infinitely many. The path integral, the sum over all histories, did not converge on a single prediction. It generated the full fractal infinity of the eternal multiverse, with every possible set of physical laws realized somewhere. The theory that was supposed to explain why the universe exists produced an answer that explained nothing. Hawking understood this, and in 2002, when he told Hertog the book was wrong, what he meant was not that the no-boundary proposal itself was wrong. He still believed in it. What was wrong was the perspective, the bottom-up perspective, where you start from some initial conditions and evolve forward using fixed, eternal laws. That perspective, applied to the no-boundary proposal, generated the infinite multiverse. The perspective had to be reversed. That reversal would take 16 years, 15 co-authored papers, and the gradual destruction of Hawking's body to complete. What emerged from it was not a minor correction. It was a new way of thinking about what physical laws are. And to understand how it was built, you need to understand the person who built it alongside him. Because the most extraordinary thing about Hawking's final theory is not what it says about the universe. It is how it was created. By two minds, one of them trapped in a body that could do almost nothing, communicating through eye movements and facial expressions, producing ideas that made the rest of the field deeply uncomfortable. Thomas Hertog was 23 years old when he first met Stephen Hawking. It was 1998, a dazzling summer day in Cambridge. Hertog had just completed the mathematical tripos, the legendary Cambridge mathematics examination, and had finished at the top of his class. There was an unwritten rule at Cambridge, a tradition that everyone understood, but nobody had made official. Whoever came top of the master's class would receive an invitation to meet Stephen Hawking. Hertog came top. Hawking invited him to his office on Silver Street. 25 years later, Hertog described that meeting with a kind of amused precision. Stephen Hawking invited me to his office, here on Silver Street, to discuss the Big Bang. That was his idea of a job interview. Hertog was born on May 27, 1975, in Belgium. He had earned his master's degree from KU Leuven in 1997, graduating summa cum laude. The meeting with Hawking led to a PhD at Cambridge, completed in 2002 with a thesis titled The Origin of Inflation. After that, postdoctoral stints at UC Santa Barbara, the Laboratoire Astroparticule et Cosmology in Paris, and a fellowship at CERN. He returned to KU Leuven as a professor in 2011, became full professor in 2014, and now heads the Institute for Theoretical Physics and directs the university's Gravity Institute. Over 115 papers, more than 5,400 citations. Those are the facts of a career. They do not tell you what the collaboration was actually like. They do not tell you what it meant to do theoretical physics with Stephen Hawking in the years when his body was failing completely. When Hertog arrived at Cambridge in 1998, Hawking could still communicate at roughly 15 words per minute using a handheld clicker connected to his speech synthesizer. The voice that came out was the iconic one, the flat robotic tone generated by a system called Perfect Paul, created by MIT's Dennis Klatt. 15 words per minute is slow, painfully slow by the standards of normal conversation. But it was workable. You could have an exchange. You could ask a question and get an answer in something approaching real time. Hawking could still participate in discussions, give lectures, supervise students. The process was laborious, but the channel was open. Then, halfway through the 20-year collaboration, Hawking lost the remaining strength in his hand. He could no longer press the clicker. The last voluntary movement available to him was a single twitch of his cheek muscle. An infrared sensor was mounted on his glasses to detect this twitch, and through it, Hawking could select characters on a screen, one at a time. His communication rate fell from 15 words per minute to approximately 1 to 2 words per minute. A single sentence could take an hour. In 2011, alarmed by further decline, Intel Labs launched a 3-year project to build Hawking a new communication system. They called it ACAT, the Assistive Context-Aware Toolkit. It incorporated predictive text technology from SwiftKey, trained on Hawking's own writings, so the system could anticipate what he was likely to say next. It reduced the number of characters he needed to input by 80% and roughly doubled his typing speed. But even with these improvements, the trajectory was one-directional. By his final years, Hawking had slowed to several minutes per word. The channel between his mind and the outside world had narrowed to almost nothing. A mind that could hold the wave function of the universe in its working memory, communicating through a system that made texting on a 1990s flip phone look instantaneous. And here is the part that should stop you. He did not slow down. The physics did not slow down. The radicalism of his ideas did not soften. If anything, as his body deteriorated further, his thinking became more ambitious, more aggressive, more willing to tear apart his own earlier work. The man who could produce perhaps a few sentences per day was producing some of the most provocative theoretical physics of the 21st century. Hertog adapted to the collapse of normal communication by developing something he describes as somewhat magical. He would position himself in front of Hawking and fire questions at him. Yes or no questions. Forced choice questions. Questions designed to narrow down a complex idea one binary step at a time. And he would read Hawking's response not from the speech synthesizer, but from his face, from his eyes. By the end, Hertog said, I could detect several levels of no and several levels of yes, with a few in between. Hawking had a very wide range of facial expressions, ranging from extreme disagreement to extreme excitement. Think about what this means. Theoretical physics, at its highest level, is a conversation between minds working at the edge of what human cognition can handle. It involves subtle distinctions, tentative hypotheses, mathematical intuitions that resist verbalization, and these two men were conducting this conversation through eye movements and facial expressions. Werner Israel, the physicist, compared Hawking's situation to Mozart composing an entire symphony in his head. But it was more constrained than that. Mozart could at least hum a melody. Hawking could twitch his cheek. And under these conditions, these two men produced a body of work that proposed something genuinely radical about the structure of reality. Not just about the multiverse, not just about inflation, about the nature of physical law itself. The technical heart of their final paper is a mathematical operation that sounds deceptively simple. They applied holography to the problem of eternal inflation. Holography, in the physics sense, is the idea that the information contained in a volume of space can be encoded on the boundary of that space in one fewer dimension. The most famous version of this idea is Juan Maldacena's ADS/CFT correspondence, published in 1997, which showed that a theory of gravity in a particular curved space-time, called anti-de Sitter space, is mathematically equivalent to a quantum field theory defined on the boundary of that space-time. Two completely different theories in different numbers of dimensions, describing the same physics. This was not a metaphor. It was a mathematical proof, and it transformed string theory overnight. What Hawking and Hertog did was apply a variant of this holographic correspondence to cosmology. Their version built on work by Andrew Strominger from 2001, who had proposed a version of holographic duality for de Sitter space, the kind of space-time that describes an expanding universe with a positive cosmological constant. But Hawking and Hertog added something that changed everything. Standard holographic correspondences relate theories with different numbers of spatial dimensions. Hawking and Hertog projected out the time dimension itself. The central equation of the paper expresses the no-boundary wave function, the probability amplitude for the universe to have a particular geometry, as being proportional to the partition function of a quantum field theory defined on the boundary surface at the threshold of eternal inflation. The wave function on one side, the partition function on the other, connected by holographic duality. What this does is replace the bulk gravitational path integral, the sum over all possible four-dimensional space-time geometries that leads to the infinite multiverse, with something far more tractable. The partition function of the boundary theory is smooth, normalizable, and finite. When they calculated it in specific toy models using an ABJM-type superconformal field theory and squashed three-sphere geometries, the results were striking. The probability distribution peaked at the round three-sphere, the most symmetric possible geometry. It strongly suppressed anisotropic geometries, and it gave essentially zero probability to geometries with negative curvature. The multiverse in this framework was not infinite, it was finite, constrained, reasonably smooth, as the paper puts it. Hawking himself said it clearly. We are not down to a single unique universe, but our findings imply a significant reduction of the multiverse to a much smaller range of possible universes. That was the headline result, and it is important. A finite multiverse is qualitatively different from an infinite one. An infinite multiverse makes prediction impossible. A finite multiverse, at least in principle, makes prediction meaningful again. It rescues physics from the abyss of unfalsifiability. But the headline result is not why this paper should keep you awake at night. The headline result is the surface. What lies underneath the surface is the operation that made the result possible. The projection of time. The replacement of a four-dimensional space-time history with a three-dimensional, timeless boundary theory. In their framework, eternal inflation is not a process that happens over time. It is reduced to a timeless state defined on a spatial surface at the very beginning. Time does not flow through the equations. Time emerges from them. As Hertog put it, when applied to cosmology, the holographic viewpoint implies that time evolution is emergent, not built in. In our theory, the universe that evolves in time emerges from a timeless state at the Big Bang. You might read that sentence and think it is a statement about mathematics, about a convenient formalism, about a choice of how to set up the equations that does not necessarily say anything about reality. Many physicists would prefer to read it that way. That is the comfortable reading, the reading that lets you nod, file the paper under interesting technical approach, and go back to your regular work. But Hawking and Hertog were not making a statement about formalism. They were making a statement about reality. And over the 20-year arc of their collaboration, they made the implications of that statement increasingly explicit. The universe, they argued, does not begin in a particular state and evolve forward according to pre-existing laws. There are no pre-existing laws. The laws emerge with the universe. They co-evolve with the cosmos. The Big Bang is not just the beginning of time, it is the beginning of physical law. And if you trace the universe backward far enough, the laws themselves dissolve. Physics fades away back into the Big Bang. That is not a slogan. That is the mathematical structure of their theory, stated in plain language. And that changes everything, because every other theory in the history of physics has assumed the opposite. Every equation Newton wrote, every field Einstein derived, every calculation in quantum mechanics and quantum field theory, and the standard model of particle physics assumes that the laws are eternal, that they existed before the universe, will exist after the universe, and are the immovable framework within which everything else happens. The entire project of theoretical physics, from Galileo to the present, has been a search for those eternal laws. Know the mind of God, Hawking wrote. Find the rules, decode the program. The assumption was always that the program existed, was written in advance, and could be read. Hawking's final theory says the program was never written in advance. It was not written at all. It emerged. It evolved. And the search for the mind of God is not a search that can succeed or fail. It is a search for something that was never there. That is the first real destination of this story. And if you are thinking that it sounds radical but essentially harmless, that it is the kind of deep philosophical point that does not affect anything practical, then you are not following the logic far enough. We will follow it further. But first, something else happened while Hawking and Hertog were building this theory. Something that threatened to destroy the entire foundation they were building on. And the fact that the debate it sparked has never been resolved tells you something important about the state of physics, something the field would rather you did not know. In 2017, the same year Hawking and Hertog submitted their final paper to the ArXiv, a team of 3 physicists published a result that hit the foundations of quantum cosmology like a wrecking ball. The team was Job Feldbrugge at the Perimeter Institute, Jean-Luc Leyners at the Max Planck Institute for Gravitational Physics, and Neil Turok, who was then the director of the Perimeter Institute and one of the most prominent cosmologists in the world. Turok had his own history with Hawking. They had collaborated, they had argued, they respected each other, and now Turok was about to publish a paper arguing that the mathematical foundations of the no-boundary proposal, the idea that had anchored Hawking's career since 1983, were fundamentally broken. Their weapon was a mathematical technique called Picard-Lefschetz theory, a rigorous method for defining oscillatory path integrals. Path integrals are the mathematical backbone of the no-boundary proposal. You sum over all possible geometries of the universe, weighted by a phase factor, and the result gives you the probability amplitude. But summing over all possible geometries is not something you can do carelessly. The integral is over an infinite dimensional space, and it oscillates wildly. The question of how to define it, how to make it well defined, which contour to integrate along, is not a detail. It is everything, and Hartle and Hawking had handled it using the Wick rotation, the replacement of time with imaginary time, which converts the oscillatory integral into a well-behaved Euclidean one. What Feldbrugge, Leyners, and Turok did was apply Picard-Lefschetz theory directly to the original Lorentzian real-time path integral without performing the Wick rotation. And what they found was that the semi-classical exponent came out with the opposite sign to what Hartle and Hawking had obtained. That does not sound dramatic if you do not work in this field. Let me tell you what it means. The no-boundary proposal was supposed to predict a smooth, orderly universe. Perturbations, the tiny fluctuations that eventually grow into galaxies and stars and planets, were supposed to start small and well-behaved. The smooth beginning of the shuttlecock geometry was supposed to guarantee this. What the Picard-Lefschetz calculation showed was the opposite. The perturbations were governed by an inverse Gaussian distribution. They were unsuppressed. They grew without bound. The smooth beginning produced a universe that immediately exploded into infinite roughness. They published 3 papers in rapid succession: Lorentzian Quantum Cosmology in Physical Review D, Volume 95, No smooth beginning for space-time in Physical Review Letters, volume 119. And No Rescue for the No Boundary Proposal in Physical Review D, volume 97. The titles alone tell you how confident they were. Turok declared through Quantum magazine, "We discovered that it just failed miserably. It was just not possible quantum mechanically for a universe to start in the way they imagined." He called the No Boundary Proposal a disaster. This was not a fringe attack. This was not a crank paper on the internet. Turok was one of the most accomplished theoretical cosmologists alive. He held the directorship of one of the most prestigious theoretical physics institutes in the world. He had collaborated with Hawking personally, and he was saying, with mathematical backing, that the idea Hawking had spent 34 years developing was not wrong in some subtle or marginal way. It was catastrophically, structurally broken. The smooth beginning of space-time was not smooth. It was infinitely rough. The No Boundary Proposal did not work. The defense came from a team that included Thomas Hertog, James Hartle, and several younger collaborators, Juan Diaz-Doronsoro, Jonathan Hallowell, Oliver Janssen, and Yannick Fraze. They published their central counter-argument in 2019 in Physical Review D, volume 99, under the title, "What is the no-boundary wave function of the universe?" And what they did in that paper was radical. They did not try to fix the path integral. They did not argue that Turok's Picard-Lefschetz calculation was wrong on its own terms. Instead, they abandoned the path integral as the defining mathematical object of the theory. Let that sit for a moment. The path integral was the heart of the no-boundary proposal. It was the mechanism by which you summed over all possible histories of the universe. It was what made the proposal a quantum mechanical theory rather than a classical one. And Hertog and Hartle's response to the Turok attack was to say, in effect, the path integral is not the theory. The theory is the wave function. And we define the wave function directly as a sum over specific saddle points satisfying regularity conditions without relying on the path integral to specify it. This was technically ingenious. By specifying the wave function directly, they sidestepped the entire question of which contour to integrate along, which was the source of the disagreement. The wave function they defined was well behaved. It produced suppressed perturbations. It predicted a smooth universe. The result was self-consistent, but it came at a cost. The path integral was supposed to provide the foundation, the justification, the reason why the wave function had the form it did. Without it, the wave function was specified by hand. It worked, but the deeper question of why it worked, why these particular saddle points and not others, was left open. Hertog acknowledged the depth of the disagreement without flinching. "We disagree with his technical arguments," he said, about Turok, "but more fundamentally, we disagree also with his definition, his framework, his choice of principles. And that is the more interesting discussion." Read that again carefully. He is not saying Turok made a calculation error. He is saying they are working in different conceptual frameworks. They disagree about what the theory is, not about the answer, but about the question. And as Natalie Wolchover documented in her June 2019 article in Quantum magazine, the debate was ultimately traced to differing beliefs about how nature works. Not differing calculations, differing beliefs. At the foundations of quantum cosmology, the most fundamental theory humans have attempted to construct about the origin and nature of the universe. The experts cannot agree on what they are even talking about. And here is what makes this worse. Neither side has won. The debate has not been resolved. It was described as heated yet friendly. Hertog himself called the no-boundary proposal a stunningly beautiful and provocative idea, even as he maintained it was mathematically incoherent. The two sides published their arguments, responded to each other once or twice, and then largely stopped engaging directly. The field moved on. Other problems attracted attention. The question of whether the mathematical foundations of quantum cosmology are sound has been left hanging, unresolved, like an open wound that everyone has agreed to stop looking at. James Hartle, the man who co-authored the original 1983 paper with Hawking, the man who helped write the wave function of the universe, was diagnosed with Alzheimer's disease in 2002 too. He died on May 17, 2230. There is a symmetry there that is almost too cruel to be accidental. Hawking lost his body, but kept his mind. Hartle kept his body, but lost his mind. The universe took both of them in different ways and left the theory they built together in a state of permanent contestation. And maybe that is the real reason the debate has never been settled. Not because the mathematics is too hard, not because the physicists involved lack the talent or the will, but because what the mathematics points toward, on both sides of the argument, is a place where mathematics itself stops working, where the equations dissolve into ambiguity, where the ground gives way. And the physicists on both sides, despite their profound disagreements about everything else, share one unspoken consensus. They would all rather work on something else. But the direction Hawking and Hertog were pointing did not depend on resolving the path integral debate. The specific mathematical machinery might be contested. The direction was not. And that direction led somewhere that most physicists would rather not go. Because what Hawking and Hertog were building over 2 decades across more than 15 co-authored papers was not just a technical fix for the multiverse problem. It was a new way of understanding what physical laws are. And to grasp why that matters, why it should keep you awake at night, you need to understand the reversal at the heart of their program, the move they called top-down cosmology. The conventional way of doing cosmology, the way it has been done since Newton, is bottom-up. You start with the laws of physics. You specify initial conditions. You evolve the system forward in time using those laws. The laws are assumed to be eternal, existing before the universe, independent of anything that happens inside it. The initial conditions are a separate problem, something to be determined by observation or by a theory of the initial state. But the laws themselves are the bedrock. They are given. They are the frame within which everything else moves. Top-down cosmology reverses this completely. Instead of starting from the Big Bang and evolving forward, you start from the present, from the observed properties of the universe, from the fact that you exist, that you are asking questions, that you are performing measurements, and you trace the histories backward. The key insight, the one that Hawking and Hertog spent years developing, is that the histories of the universe depend on the question being asked. They depend on what is being observed. This is not mysticism. It is the structure of quantum mechanics applied at the cosmological scale. In quantum mechanics, the act of measurement selects an outcome from a superposition of possibilities. In top-down cosmology, the act of observation selects a history from the superposition of all possible cosmic histories encoded in the no-boundary wave function. Hawking described it with characteristic directness. Top-down cosmology is a framework in which one essentially traces the histories backwards from a space-like surface at the present time. The no-boundary histories of the universe thus depend on what is being observed, contrary to the usual idea that the universe has a unique, observer-independent history. That last phrase is the one that should disturb you. Contrary to the usual idea that the universe has a unique, observer-independent history, physics has assumed for 400 years that the universe has a history, that things happened, that the Big Bang occurred, that atoms formed, that stars ignited, that planets coalesced, and that all of this happened whether anyone was watching or not. The observer-independent history of the universe is not a minor assumption. It is the assumption that makes science possible. If the history depends on the observer, if different observations select different histories, then whose history is the real one? Hawking and Hertog's answer was that no history is the real one. All histories contribute. The wave function encompasses all of them, and the particular history you experience is not determined by some objective initial condition at the Big Bang. It is determined by the fact that you are here, now, asking this specific question, making this specific observation. Your observation retroactively shapes the outcome of the Big Bang, not in the sense that you travel back in time, in the sense that the quantum mechanical amplitude for the present state of the universe is computed by summing over all histories consistent with what you observe, and the past that emerges from this calculation depends on the present. This echoes something that the American physicist John Archibald Wheeler had proposed decades earlier. Wheeler, who coined the terms black hole and wormhole, who supervised both Richard Feynman and Hugh Everett, who was one of the most creative minds in 20th century physics, had spent his later years developing what he called the participatory universe, the idea that observation does not merely reveal reality, but partially constitutes it, that the universe is not a machine running according to a pre-written program, but a participatory process in which observers play a necessary role. Wheeler illustrated this with his famous delayed choice experiment, which showed that a measurement performed today can determine the path a photon took in the past. The future, in some quantum mechanical sense, reaches back and shapes history. Hawking admired Wheeler, and top-down cosmology is, in a meaningful sense, Wheeler's participatory universe, made mathematically precise, applied not to a single photon in a laboratory, but to the entire cosmos. The observer does not merely discover the universe. The observer participates in its definition. But Hawking and Hertog went further than Wheeler, much further. Wheeler had proposed that observation plays a constitutive role in reality. Hawking and Hertog proposed that this role extends to the laws of physics themselves. The laws are not eternal. They are not written in advance. They emerge with the universe through the same quantum mechanical process that determines its history. Trace the universe backward, and you do not approach a set of primordial laws that govern the Big Bang. You approach a state where the distinction between different laws becomes meaningless, where the laws, like time, dissolve. Thomas Hertog has a phrase for this. He calls it profoundly Darwinian, and the word choice is deliberate. Hertog titled his book On the Origin of Time, a conscious echo of Darwin's On the Origin of Species. The parallel is precise. Before Darwin, the diversity of life was assumed to reflect a pre-existing design, a blueprint. The species were fixed, created according to a plan, and the job of the naturalist was to catalogue and understand that plan. Darwin showed that there was no plan. The species were not fixed. They emerged through a process of random variation and natural selection, without foresight, without design, without any external blueprint at all. Hawking and Hertog's claim about physics is structurally identical. Before their work, the laws of physics were assumed to reflect a pre-existing mathematical structure, a blueprint. The laws were fixed, eternal, and the job of the physicist was to discover them. Hawking and Hertog are saying there was no blueprint. The laws emerged through a process that Hertog describes as akin to Darwinian evolution. Random variation among quantum possibilities, selected by the fact of observation. No foresight, no design, no external framework. Hertog writes in his book that he and Hawking came to see the Big Bang not only as the beginning of time, but also as the origin of physical laws, a process of random variation and selection akin to Darwinian evolution. And Hawking told him, in what may be the most important single sentence he ever uttered about physics, "We are not angels who view the universe from the outside. Our theories are never decoupled from us." That sentence ends the search for the mind of God, not with a failure, not with an admission that the question is too hard, with the recognition that the question was wrong. There is no view from outside. There is no God's eye perspective on the laws of nature. There are no laws of nature in the traditional sense of that phrase. There are patterns, emergent, evolving, observer-dependent patterns that arose with the cosmos and are inextricable from the act of observing it. The universe is not a machine governed by a program. It is, in Hertog's phrase, a self-organizing entity, closer to a living system than to a clockwork mechanism. And here is where the comfortable reading of this theory breaks down entirely. Because if the laws of physics are emergent rather than eternal, if they arose through a process rather than being imposed from outside, then there is nothing that guarantees their permanence. Nothing that says the patterns we call laws must remain stable. Nothing that says the forces holding your atoms together, the constants governing nuclear reactions, the gravitational coupling that keeps planets in orbit, must continue to hold tomorrow in the same way they hold today. This is not science fiction. This is the logical endpoint of the published, peer-reviewed work that Stephen Hawking spent the last 2 decades of his life building. If laws are born with the universe, then they are contingent, they are historical, they are products of a process, and products of a process can, in principle, change. The bedrock on which physics stands, on which chemistry stands, on which biology stands, on which your body and your brain and every atom in your body stands, is not bedrock. It is a pattern that emerged from a quantum process at the beginning of time. And patterns, unlike laws, do not come with guarantees. You might object that this is philosophical overreach, that whatever the mathematical formalism says, the laws of physics have been stable for nearly 14 billion years, and there is no empirical evidence that they are changing now or that they ever will. And that is true. The laws appear stable. Every measurement we have made, from the fine structure constant measured in distant quasars to the proton to electron mass ratio measured in molecular hydrogen at high redshift is consistent with the constants of physics being the same today as they were billions of years ago. But that is not the same thing as saying they are guaranteed to be the same. A law that is eternal by definition cannot change. A pattern that emerged from a process might be extraordinarily stable over timescales that dwarf the age of the universe, and still not be guaranteed. The distinction between has not changed and cannot change is the distinction between an observation and a principle. And Hawking's final theory says, the principle is gone. What remains is only the observation. That should unsettle you, not because a change in the laws of physics is likely. There is no evidence it is happening, or that it will happen in any timescale relevant to human civilization, but because the conceptual ground beneath physics has shifted. The assumption that sustained 4 centuries of scientific progress, from Galileo's falling bodies to the detection of gravitational waves, was that the laws are eternal, and the job of the physicist is to find them. If Hawking and Hertog are right, that assumption was always wrong. The laws were never eternal. They were never there to be found in the way physicists imagined. The search for the mind of God was not a search that could be completed. It was a category error, an attempt to find something that the universe, in its deepest structure, does not contain. Hawking knew this. He published it. He signed off on the final corrections 10 days before he died. The most famous scientist of his generation, communicating through the last twitch of his cheek, used his final act of scientific agency to tell the world that the foundational assumption of physics is wrong. And then he died. And then the world did something that, if you understand what the paper actually says, is almost incomprehensible in its inadequacy. The paper was published on April 27, 2018, in the Journal of High Energy Physics. It was open access, meaning anyone could read it without paying a cent. The media picked it up immediately, mostly because Hawking had just died, and the narrative of a final paper, a last scientific act, from the most famous physicist since Einstein, was irresistible. BBC covered it, CNN covered it, The Guardian, The Washington Post, Newsweek, Popular Science, Space.com. For a brief window, it was everywhere. But the coverage was wrong. Almost all of it. Outlets suggested the paper would let scientists prove the multiverse exists, or detect other universes, or that it was the most important thing Hawking had ever done. The actual paper is a 14-page toy model using a specific class of holographic field theories applied to simplified geometries. It describes a framework, not a finished product. Hawking and Hertog themselves acknowledged that the work needed what they called a significant extension of holographic cosmology to more realistic cosmologies. The media treated it as a revelation. It was actually a blueprint, a direction, a first sketch of something that would take decades more work to develop fully. The physicists who were asked to comment were more measured, and some were brutal. Frank Wilczek, who won the Nobel Prize in 2004 for his work on the strong force, said the paper was heavy on speculative assumptions and that he did not see any concrete predictions. He added that it relied on several speculative and unproven theories and used them in bold ways to make vague conclusions. Neil Turok, who by then had published his own devastating critique of the no-boundary proposal's mathematical foundations, told the Sunday Times that he remained puzzled as to why Hawking found this picture interesting. Katie Mack pointed out that the ideas in the paper were not giving any new kind of signature different from other models of inflation, and she explicitly debunked the media claims about proving the multiverse. Will Kinney at the University of Buffalo noted that Hawking and Hertog did not even suggest any ways to see evidence of the multiverse, meaning their theory remained untestable. There was some praise. Carlos Frenk, the cosmologist, called the prospect of finding imprints of other universes in our cosmic background radiation breathtaking. André Linde, the pioneer of eternal inflation, acknowledged that Hawking had approached one of the most important and challenging problems of modern physics. But even Lind added that the approach was based on conjectures that the authors had formulated but not proved. And that was it. The cycle ran its course. The media coverage faded. The physics community noted the paper, cited it where relevant, and returned to other problems. As of now, the paper has accumulated several hundred citations, a respectable number for a theoretical physics paper, but not the kind of impact you would expect from a work that implies the laws of physics are not eternal. There was no crisis summit, no urgent follow-up program by the broader community, no front-page reckoning with the implications. Compare this to what happened when the BIC EP2 experiment announced in 2014 that it had detected primordial gravitational waves, evidence that would have confirmed inflation. That announcement made global headlines. It was on the front page of every major newspaper. Physicists wept on camera. The result was later retracted. The signal turned out to be galactic dust, but the reaction showed what happens when the physics community believes a result matters. The machinery of attention activated immediately. Papers were written, conferences were organized, careers were redirected. Nothing like that happened for Hawking's final paper. And the reason it did not happen is not that the paper is unimportant. The reason is that the paper is threatening. Not threatening in the way a competing theory is threatening, where the question is simply, whose equations are better? Threatening in a deeper sense. Threatening to the foundational assumption that makes the entire enterprise of theoretical physics feel meaningful. If the laws of physics are eternal, then the physicist's job is to discover them. That is a noble, exciting, meaningful pursuit. You are uncovering the hidden structure of reality. You are reading the code that the universe runs on. Every equation you derive brings you closer to the ultimate truth. The search has a destination. It has a finish line. It can succeed. If the laws of physics are emergent, if they arose with the universe through a process of quantum evolution, then the physicist's job is different. You are not discovering eternal truths. You are describing patterns that happen to hold in this particular epoch of this particular universe's history. The patterns are real. They are extraordinarily stable. They are the foundation of all technology, all chemistry, all biology. But they are not eternal. They are not the ground floor. There is no ground floor. There is only the pattern, and beneath it, the quantum process from which it emerged, and beneath that, the dissolving of physics itself back into the Big Bang. That is a profoundly less satisfying story. It is also, if Hawking and Hertog are right, the true one. The discomfort this creates is not something physicists talk about openly. You will not find a prominent theorist saying, "I am afraid that the laws of physics might be contingent," but you can see the discomfort in the way the paper was received. The praise was qualified, the criticism was dismissive, and the silence, the vast silence of the broader community, was the loudest response of all. Thomas Hertog did not stop. After Hawking's death, he continued the program. He secured a major European Research Council grant titled Euclidean Holography for Cosmology, running from August 2021 through October 2026. His group at KU Leuven has published a steady stream of papers extending the original framework. In 2023, Hertog, Janssen, and Carlson published a paper in Physical Review Letters applying the Kontsevich-Segal criterion to the no-boundary state, showing it acts as a mathematical selection mechanism on inflationary potentials. In 2025, Hertog, Pohls, and Venken published Holographic Eternal Inflation in the Journal of High Energy Physics, directly extending the original 2018 paper by identifying specific, complex deformations of the ABJM field theory, for which the partition function specifies the amplitude of an eternally inflating universe. This moved beyond the toy models of the original paper toward more concrete holographic realizations. Juan Maldacena himself, the physicist whose AD/CFT correspondence is the foundation of modern holography, entered the discussion in 2024 with a paper titled Comments on the No-Boundary Wave Function and Slow Roll Inflation. The program is alive. It is growing, quietly in the background, while the rest of the field works on other things, and connections are emerging that no one anticipated. Hertog's 2025 paper revealed a convergence between the holographic no-boundary framework and the swampland conjectures, a separate program in string theory that attempts to constrain which low-energy theories can be consistently embedded in quantum gravity. The holographic constraints on the no-boundary state naturally exclude the same regimes that violate the swampland's cobordism conjecture. Two different programs developed independently, arriving at the same boundaries. That is the kind of convergence that in the history of physics has usually meant something is right. But you have not heard about any of this. You have not heard about the Kontsevich-Segal paper. You have not heard about the holographic eternal inflation extension. You have not heard that Maldacena himself is now engaged with this framework. You have not heard that the swampland conjectures are converging with Hawking's final theory. You were told in 2018 that Hawking published a last paper that it had something to do with the multiverse, and that some physicists thought it was speculative. That was the extent of the public accounting, and the actual content of the paper, the thing it implies about the nature of physical law, has never been reckoned with outside a small circle of specialists. Hertog wrote the book Hawking asked him to write, On the Origin of Time, published in April 2023. 352 pages. It became a New York Times bestseller. Hertog laid out the full arc of the 20-year collaboration, the philosophical implications, the vision of a universe where laws evolve and physics fades away. Even Neil Turok, who had called the no-boundary proposal a disaster, praised the book as a beautifully written, thought-provoking account. The book ends with an image that captures the weight of everything Hawking and Hertog built together. Hawking's ashes were interred at Westminster Abbey on June 15, 2018. More than 1,000 people attended. Another 1,000 members of the public were selected by ballot from 25,000 applicants. His ashes were placed in the scientists' corner between the graves of Isaac Newton and Charles Darwin. Newton and Darwin. Think about what that placement means. Newton gave us the idea that the universe is governed by eternal mathematical laws, that nature is a machine and the laws are its program, that the physicist's job is to find the program and read it. Darwin gave us the idea that the diversity of life is not the product of design, but of a blind process, that there is no blueprint, that patterns emerge from randomness and complexity arises from simple rules iterated over deep time, without foresight, without purpose. Hawking's final theory says the universe is closer to Darwin's vision than to Newton's. The laws of physics are not a program written in advance. They are patterns that emerged from a process. They evolved. They are contingent. They are historical. And the man who told the world that the ultimate triumph of physics would be to know the mind of God spent his last years working toward the conclusion that there is no mind to know. His ashes sit between the two men whose ideas define the poles of that debate, between the eternal and the emergent, between the designed and the evolved, between the laws and the patterns. And the placement, whether intended or not, is the most precise possible summary of what Hawking's final theory means. But that image, as precise as it is, lets you off the hook too easily. It frames the story as a debate between intellectual traditions, Newton versus Darwin, eternal laws versus emergent patterns, a question for philosophers and theoretical physicists to argue over in seminar rooms and book reviews, something you can appreciate from a comfortable distance, something you can nod at and move on from, something you can find interesting without it touching you. That distance is an illusion, and the reason it is an illusion is the same reason the physics community chose not to engage with this paper in the way it deserves. Because the moment you let this idea get close to you, the moment you follow the logic past the seminar room and into your actual life, it stops being a philosophical debate and starts being something you cannot unfeel. It touches you. And to understand why, you need to look more carefully at the burial itself. Because the burial was not negligence. It was not an oversight. It was not the physics community being too busy to pay attention. The physics community pays attention to things that matter. When the Higgs boson was discovered at CERN in 2012, the response was instantaneous and global. When LIGO detected gravitational waves in 2015, the Nobel Prize followed in 2 years. When BIC EP2 announced its retracted result in 2014, every major cosmology group on Earth redirected resources within weeks. The machinery of attention exists. It functions. It is activated when the community collectively decides that a result demands engagement. That machinery was not activated for Hawking's final paper, and the reason was not that the paper is unimportant. It was that the paper is the wrong kind of important. The Higgs boson confirmed a prediction. Gravitational waves confirmed a prediction. Even the BIC EP2 result, had it been real, would have confirmed a prediction. These are results that validate the framework, that tell the community it is on the right track, that reward the program. Hawking's final paper does the opposite. It questions the framework. It suggests that the entire enterprise of looking for eternal laws, the search that has defined theoretical physics for 4 centuries, may be built on a category error. That does not earn attention. That earns silence. Neil Turok's trajectory is instructive here. Turok published his devastating critique of the no-boundary proposal in 2017 and 18. He called it a disaster. He said it was not possible quantum mechanically for a universe to begin the way Hawking and Hertog imagined. And then he walked away, not just from the no-boundary proposal, from the entire inflationary paradigm. Turok moved from the Perimeter Institute to the University of Edinburgh in 2020, taking up the inaugural Higgs Chair of Theoretical Physics, and began working with Latham Boyle on a radically different model. ACPT symmetric mirror universe, in which a partner universe extends backward in time from the Big Bang, a mirror image of our own, and inflation is not needed at all. He abandoned the field that Hawking's paper was trying to fix. He did not try to repair the foundations. He left the building. That is a pattern you see across the community's response to the crisis that Hawking's paper addresses. The physicists who engage with the eternal inflation problem either propose radical alternatives like Turok's mirror universe, or they accept the infinite multiverse and the anthropic principle and stop worrying about falsifiability, or they focus on narrow technical problems where progress is still possible without confronting the foundational question. What almost nobody does is engage directly with the claim that the laws of physics are emergent. That claim is not attacked. It is not refuted. It is simply not discussed. And that silence has a structure to it. It is the silence of a community that cannot afford to engage. Because the moment you seriously entertain the possibility that the laws are emergent, you are not just questioning one paper or one framework. You are questioning the assumption that makes your entire career feel meaningful. You are questioning whether the equations you spend your life deriving are discoveries about reality or descriptions of a pattern that happens to hold. The answer might be the same either way. The equations still work. The predictions still come out right. The technology still functions. But the meaning changes, and meaning is not something physicists like to admit they need. There is another misconception that needs correcting here, one that has muddied the public understanding of Hawking's work for decades. You have probably heard that the no-boundary proposal means the universe had no beginning. That is not quite right. The no-boundary proposal does not say the universe has no beginning. It says the universe has a beginning that is not a boundary. The beginning is not a moment in time before which there was something else. It is a smooth, geometric cap, like the South Pole of the Earth, where time ceases to be a meaningful coordinate. There is a beginning. There is a first moment. But the question, what happened before the first moment, is not a question that refers to anything. It is grammatically correct, but physically empty, the way what is north of the North Pole is grammatically correct, but geographically empty. This matters because Hawking and Hertog's final theory goes further. In their holographic reformulation, the beginning is not just a smooth cap. It is a boundary where time emerges from a timeless state. The universe does not begin in time. Time begins in the universe. And the laws of physics do not govern the beginning. They emerge from it. The beginning is not governed by anything. It is the point where governance itself comes into being. Below the beginning, or rather at the beginning, there is no time, no law, no physics. There is a quantum state from which all three arise, and the particular time, particular laws, and particular physics that emerge depend, in the top-down framework, on the observations being made at the present. This is where the comfortable version of the story, the version where Hawking's final paper is an interesting theoretical contribution that may or may not be correct, starts to collapse. Because if you take this seriously, if you follow it honestly, then you end up somewhere that is genuinely unsettling. Not unsettling in the way that a large number is unsettling, or a distant black hole is unsettling, or the scale of the observable universe is unsettling. Those are the pleasant kind of unsettling. The kind that makes you feel small, but in a way that is ultimately reassuring, because the vastness is governed by rules you can understand. This is the other kind. The kind where the rules themselves are in question. And the reason it touches you is something that neither the media coverage, nor the physics community, nor even Hertog's book has stated with the bluntness it deserves. You depend on the laws of physics being stable, not in an abstract philosophical sense, in the sense that every atom in your body is held together by the electromagnetic force, and the electromagnetic force has a specific strength measured by a number called the fine structure constant, and that number is approximately 1 divided by 137. If that number were different by a few percent, atoms would not form, chemistry would not work, and you would not exist. Not you in some hypothetical future sense. You, right now, reading this, your continued existence from 1 second to the next depends on that number being what it is. And under the traditional framework of physics, the framework that has governed the discipline since Newton, that number is a law. It is eternal. It was the same at the Big Bang as it is now, as it will be in 1 trillion years. It is written into the fabric of reality. It cannot change. It does not change. It is, in the deepest sense, safe. Under Hawking and Hertog's framework, that number is a pattern. It emerged with the universe. It arose from a quantum process at the beginning of time. It has been extraordinarily stable for nearly 14 billion years, and every measurement we have ever made, from the spectra of distant quasars to precision laboratory experiments, is consistent with it being constant. But the reason it is constant is not that some eternal law decrees it. The reason it is constant is that the pattern has held so far. The word "so far" is doing a lot of work in that sentence, and the fine structure constant is only one number. There are roughly 25 free parameters in the standard model of particle physics. The masses of the quarks, the masses of the leptons, the strength of the strong force, the weak force, the electromagnetic force, the Higgs vacuum, expectation value, the cosmological constant. Each one of these numbers is measured to extraordinary precision. Each one is consistent with being constant across the observable history of the universe, and each one, under the traditional framework, is eternal, given, a feature of the mathematical structure of reality that could not have been otherwise. Under Hawking and Hertog's framework, every single one of these numbers is a pattern, emerged, contingent, stable so far. The entire standard model, the most precisely tested theory in the history of science, with predictions confirmed to 11 decimal places, is not a window into eternal truth. It is a description of a pattern that has held for a very long time in this particular universe. And the question, why does the fine structure constant have this specific value, does not have an answer that terminates in because the laws demand it. It terminates in because that is the pattern that emerged from the quantum state at the beginning. Full stop. There is no deeper why. There is no foundation beneath the foundation. The pattern is the bottom. This is not a fringe interpretation. This is the published, peer-reviewed implication of 20 years of collaborative work by the most famous physicist of the modern era. And the distinction between a law and a pattern is not academic. A law cannot change by definition. A pattern can change in principle. The practical difference might be zero. The constants might hold for durations that dwarf the age of the universe by factors of trillions. But the conceptual difference is total. It is the difference between living in a house with a foundation and living in a house that happens to be sitting on stable ground. The house feels the same from the inside until the ground shifts. You might ask whether there is any evidence that the constants have changed. The answer is that physicists have been looking for exactly this, and the results are stringent. John Webb at the University of New South Wales led a team that reported in 2010 and 2011 using quasar absorption spectra from the Keck and VLT telescopes, a possible spatial variation in the fine structure constant at the level of a few parts per million. The result was controversial and has not been confirmed by subsequent studies. The current consensus is that the fine structure constant has been stable to within a few parts per 10 billion over the last roughly 10 billion years. That is an extraordinarily tight constraint. It means that if the constant is changing, it is changing so slowly that we cannot detect it with our best instruments across most of the observable history of the universe. But notice what that measurement tells you and what it does not. It tells you the constant has not changed by a detectable amount. It does not tell you it cannot change. It does not tell you it is prohibited from changing. It constrains the rate. It says nothing about the category, and the category is what Hawking's final theory changed. Under the old framework, asking, can the fine structure constant change, is like asking, can 2 + 2 = 5? The answer is no by definition, and the question is incoherent. Under the new framework, asking, can the fine structure constant change, is like asking, can the climate change? The answer is yes, in principle, and the relevant question becomes how fast, under what conditions, and what would trigger it. Nobody knows the answer to that question. Nobody has even begun to seriously investigate it within the framework Hawking and Hertog built. Because to investigate it, you would first have to accept the framework. And accepting the framework means accepting that the stability of physical law is an empirical fact, not a logical necessity. That it is something that needs to be explained, not something that can be assumed. And the physics community, for reasons that have more to do with psychology than with evidence, has not been willing to take that step. There is one more layer to this, and it is the one that I suspect Hawking understood better than anyone, because he had more reason to understand it than anyone. Hawking lived for 55 years with a disease that was supposed to kill him in 2. He was diagnosed with ALS in 1963 at the age of 21. His doctors gave him 2 years. He died in 2018 at 76. That is not a rounding error. That is a medical impossibility so extreme that it was studied in the Lancet Neurology as a case of extraordinary survival. The most important factor, according to the analysis, was his young age at onset. His predicted 10-year survival probability at the time of diagnosis was 94%, far higher than typical ALS patients. But even accounting for that, his survival was an outlier among outliers. His continued existence depended on a web of support systems, each one contingent, each one fragile. After a tracheostomy in 1985, more than half of his remaining years of survival were attributed to invasive ventilation and intensive supportive care. He required 24-hour nursing by the end. A team of carers, assistants, students, and collaborators maintained the infrastructure that kept his mind connected to the world. Remove any single piece of that infrastructure, and the connection breaks. It was not a life sustained by natural law. It was a life sustained by human effort, technological intervention, and a series of fortunate contingencies that could have gone differently at any stage. And during those 55 years, his body was progressively destroyed. His muscles failed one by one. His speech was taken. His ability to write was taken. His ability to move his hands was taken. His ability to move anything except a single muscle in his cheek was taken. He maintained a full week of teaching and research. Even in his final years, he supervised 39 PhD students over the course of his career. He still ate lunch with students several times per week. His disability had forced him to develop compensatory methods, seeing equations in terms of geometry, holding complex calculations entirely in his head. Former students described working with him as high risk, high gain. He needed collaborators to develop and complete research projects, but his ability to identify the right question was unmatched. Days before he died, Malcolm Perry called to update him on their soft hair work, the other major project of Hawking's final years, addressing the black hole information paradox. Perry did not know how ill Hawking was. He was put on loudspeaker. It was very difficult for Stephen to communicate, Perry recalled afterward. When I explained where we had got to, he simply produced an enormous smile. I told him we had got somewhere. He knew the final result, an enormous smile from a man who could barely move. That was the last scientific communication recorded from Stephen Hawking. Not a word, not a sentence, a smile. And through all of it, through every stage of the collapse, his mind remained intact. ALS does not typically affect cognition. The mind is preserved while the body is consumed. Hawking was fully aware at every stage of exactly what was happening to him. He could think, but he could not act. He could compose symphonies in his head, but he could not hum a single note. That experience, I believe, shaped his final theory in ways that go beyond the mathematics. Because Hawking knew, more intimately than any other physicist who has ever lived, what it means to depend on something that is not guaranteed. He depended on his body. His body failed. He depended on his hands. His hands failed. He depended on his voice. His voice failed. He depended on his cheek muscle, the last remaining connection between his mind and the outside world. And even that was fading when he died. At every stage, the thing he depended on turned out to be contingent, temporary, a pattern that held until it did not. Most physicists experience the world from inside a functioning body. They write equations with their hands. They discuss ideas with their voices. They walk to the chalkboard. They gesture. They sketch diagrams on napkins. The physical infrastructure of their work is invisible to them, the way the physical infrastructure of your daily life is invisible to you. You do not think about your legs when you walk. You do not think about your lungs when you breathe. The systems work. They have always worked. They will continue to work until they do not. And Hawking, who watched every one of those systems fail, one by one, over 55 years, had a relationship with contingency that no other physicist could match. He understood in his body what it means for a system to be stable for a long time and then to change. He understood what it feels like when the pattern holds and holds and holds and then breaks. And he produced a theory that says the same thing about the universe itself. And his final theory says the same thing about the laws of physics. They are a pattern that has held. They are not guaranteed to hold. The ground beneath physics is not bedrock. It is a pattern. And Hawking, who had spent 55 years watching the ground beneath his own body give way, one muscle at a time, was perhaps the only physicist in the world who could have arrived at that conclusion without flinching from it. Hertog saw this connection. In interviews, he has spoken about how Hawking's physical condition informed his scientific perspective, though he frames it carefully, as any good physicist would. But the resonance is unmistakable. A man whose body was the ultimate demonstration of contingency, of the fragility of patterns that seem permanent until they fail, producing a theory that says the universe itself rests on the same kind of contingency, that the laws governing atoms and stars and galaxies are, at the deepest level, no more guaranteed than the laws governing the firing of motor neurons in a human body. Both are patterns. Both have held. Both, in principle, can fail. There is a temptation here to reassure you, to tell you that the laws of physics are almost certainly stable, that there is no practical danger, that the patterns have held for nearly 14 billion years and will hold for trillions more. And all of that is probably true, but probably is not the word that used to apply. The word that used to apply was necessarily. And Hawking's final theory took that word away. You might wonder why this matters. If the practical consequences are negligible, if the constants are not changing by any amount we can detect, if the ground is not currently shifting, then who cares whether the stability of the laws is necessary or merely factual? Why does the category matter if the result is the same? It matters because the category determines the kind of universe you live in. If the laws are eternal, you live in a universe with a flaw, with a bottom, with a foundation that cannot give way. The universe might be vast and terrifying and indifferent, but at least its rules are permanent. At least the stage is fixed. Even if the play is uncertain, you can stand on that. You can build on that. You can trust it. Every bridge you have ever crossed was designed by engineers who trusted it. Every medicine you have ever taken was developed by chemists who trusted it. Every satellite in orbit, every nuclear reactor, every MRI machine, every semiconductor in every phone, in every pocket on this planet, works because physicists trusted that the laws governing electrons and photons and nuclei are the same today as they were yesterday and will be the same tomorrow. That trust is the invisible foundation of technological civilization. Nobody talks about it because nobody needs to. It is assumed. If the laws of physics are emergent, that trust is not wrong. It is justified by nearly 14 billion years of evidence. But it is trust, not certainty. It is an inference from observation, not a deduction from principle. And there is a difference. There has always been a difference, though it has never mattered until now, because until Hawking and Hertog, no serious theoretical framework suggested that the distinction was real. Other physicists had speculated about varying constants. Paul Dirac proposed a time-varying gravitational constant in 1937. Various models of quintessence and dynamical dark energy allow for slowly evolving cosmological parameters. But none of these proposals attacked the concept of law itself. They proposed that specific constants might vary within a fixed legal framework. Hawking and Hertog proposed that the framework is not fixed, that the framework is the thing that evolves. That is a different kind of claim entirely. If the laws are emergent, you live in a universe without a flaw, a universe where the rules are real, but not permanent, where the stage itself is part of the performance, where the distinction between the laws and the things governed by those laws dissolves at the deepest level, where there is no ground beneath the ground, where the question, why these laws, does not have an answer that terminates in something eternal, because there is nothing eternal for it to terminate in. There is only the pattern, and the pattern is all there is. That is the universe Hawking's final theory describes. A universe without bedrock. A universe where the laws of physics are born, evolve, and could, in principle, die. A universe closer to Darwin than to Newton. A universe that does not run on a program, but emerges moment by moment from a process that has no external author. And the man who told us this, who signed his name to this conclusion 10 days before he died, who communicated it through the twitch of a cheek muscle, did not do it carelessly. He did it after 20 years of work. 15 co-authored papers, a collaboration sustained through the most extraordinary physical constraints any scientist has ever worked under. A theory built in eye movements and facial expressions. A conclusion that cost him his own legacy. Because the Stephen Hawking the public remembers, the man who promised to reveal the mind of God, is not the Stephen Hawking who actually existed at the end. The man who actually existed had moved past that promise. He had dismantled it. He had replaced it with something harder, colder, more honest, and more disturbing. The physics community received this with a shrug. The media covered it for a week and moved on. The public was never told what the paper actually means. You were told Hawking published a last paper about the multiverse. You were not told that the paper's deepest implication is that the laws of physics are not what you think they are, that they are not permanent features of reality, but patterns that emerged from a quantum process at the origin of time, that the stability you take for granted, the reliability of gravity, the constancy of atomic structure, the predictability of nuclear reactions rests not on eternal law, but on a pattern that has held for nearly 14 billion years, and that nothing, no theorem, no principle, no mathematical proof, guarantees will hold for 14 billion more. That is what Hawking found. That is what he published. That is what the physics community quietly filed away and chose not to confront. And if you are disturbed by this, if the ground feels less solid than it did 2 hours ago, if the word pattern now carries a weight it did not carry before, then you are feeling what Hawking felt, what Hertog felt, what anyone feels when they follow this logic all the way down and realize there is nothing at the bottom. Not nothing in the sense of emptiness, nothing in the sense of no foundation, no flaw, no final answer, just the pattern holding. For now, Hertog is still at KU Leuven. The ERC grant runs through 22,000. The papers keep coming. The framework is being extended, refined, tested against other programs. The swampland conjectures continue to converge. Maldacena is engaged. The mathematics is growing more sophisticated, more concrete, less toy-like, and none of it is front-page news. None of it is being reckoned with by the public or by the broader scientific community with anything approaching the seriousness it warrants. In a better world, the program Hawking and Hertog built would be one of the central topics in theoretical physics. It addresses the single deepest question the field faces. Not what are the laws, not how do the laws work, but what are the laws made of? Where did they come from? And what guarantees that they remain? Those questions have never been more urgent. The crisis of falsifiability in cosmology has not been resolved. The string landscape has not been tamed by any other approach. The anthropic principle remains as philosophically unsatisfying as it was when Hawking rejected it 2 decades ago. And the one program that directly addresses these problems, that offers a concrete mathematical framework for replacing the infinite multiverse with a finite one, and for understanding the laws of physics as emergent rather than eternal, is being pursued by a single research group in Belgium, funded by a single grant, building on the work of a dead man who communicated his final ideas through the twitch of a cheek. Hawking asked Hertog, near the end, to try to tame the multiverse. Hertog has spent the years since Hawking's death doing exactly that, working alone now, without the mind that started the project, without the eyes that communicated agreement and excitement, and the subtle gradations between yes and no, working with the notes, the papers, the shared understanding built over 20 years of collaboration, conducted under conditions that would have broken most people in the first month. The theory is unfinished. The toy models need to be extended to realistic cosmologies. The mathematical foundations are still contested. The debate with Turok's camp has never been resolved. The testable predictions, if they exist, are decades away from being tested. The LISA Gravitational Wave Observatory, which Hertog has identified as the most promising instrument for detecting primordial gravitational waves that could confirm the theory, is not scheduled to launch until approximately 2034, 8 more years. And even then, the predictions of this framework may not be distinguishable from those of other inflation models. That was Katie Mack's critique, and it has not been answered. So the program continues in a kind of limbo, too rigorous to dismiss, too unfinished to confirm, too threatening to engage with, too important to ignore. And the man who started it is dead, his ashes resting between the two figures whose legacies define the question his final theory asks. But the direction is set, the arrow points one way, and every new result, from holographic eternal inflation to the Kontsevich-Segal criterion to the swampland convergence, points the same way, toward a universe where laws are born, not given, where physics emerges from something deeper, where the ground is not ground. Stephen Hawking corrected his last paper on March 4th, 2018. He died on March 14th. His ashes were interred on June 15th between Newton and Darwin. After the ceremony at Westminster Abbey, his voice, the flat, synthetic voice that the whole world recognized, the voice of a man who could no longer speak, was set to music by the Greek composer Vangelis and beamed into space from a European Space Agency satellite dish. The signal was aimed at 1A062100, the nearest known black hole, approximately 3,000 light-years away. His last words, broadcast into the void, will travel at the speed of light for 3,000 years before reaching their destination. By then, the signal will have degraded. The photons will have scattered, the message will be barely distinguishable from noise, but the black hole will still be there. It will have grown slightly, absorbed slightly more matter, its event horizon expanded by a margin too small to measure. And inside that horizon, in the place where the laws of physics as we understand them break down completely, where space-time itself ceases to function, the question Hawking spent his life asking will still be hanging, unanswered, in the dark. What are the laws of physics? Are they eternal? Or are they, like everything else, just passing through?